Hello, welcome to this tutorial where I'm going to show you how to work out polar coordinates. I've just tried to record this video and my diagram became stupid. This doesn't illustrate anything, so I stopped it and re-recording now. So let's just delete this. So polar coordinates, all that means is when you want to find the x and y location of a point on the screen according to an angle that you're changing, so like clock hands, something like that, and you wanted to find the end point of your hands just by changing the angle. So this will be really useful if you'll say you've got a vehicle or a spacecraft or something and you're trying to rotate it around and you want to find out exactly where it's going to be. I'm also going to show you how to do polar coordinates in 3D, and I can't find any videos that just show you it nice and quickly and easily. So I'll hopefully put a link, if I remember, in the comments or description somewhere, for if you're just interested in the 3D polar coordinates, you can go straight to that part in the video. Okay, so starting from 2D, let's just draw a quick diagram. Let's go in white. So polar coordinates, let's say you've got a simple coordinate. How did that happen? You've got a simple coordinate system. There we go, in 2D. So you've got your x-axis and you've got your y-axis, and we've got, let's say, a radius here. There we go. And then you've got a little point over here. And of course, that point, which could be an object, it could be the end of a clock hands, whatever, could be an AI pet, it's up to you. It's going to have an x position and a y position, or rather an x number and a y value, x and y values, which will describe it. So it could be 33 and then y is about 34. There you go. So x 33, y 34 at this current position. And at the moment we can see there's an angle involved here. There we go, we've got this angle that doesn't show up very well. Let's go bright green. There we go. We've got an angle, which we can now see, and we're going to label this with this little Greek letter called theta. Theta. There we go, like that. Theta. And that just means angle. Angle. I think angles usually start over here. Mathematicians love starting it that way and then going around anti-clockwise or counter-clockwise, like that. I'm used to just doing, I'm used to starting in the vertical and then going around clockwise. Makes more sense. Anyway, if things start to go wrong and you're wondering why on earth am I starting over here and things like that, it might be the mathematical settings in the computer or the library that you're using. So look out for that. Anyway, theta is our angle and it's about, what, 45 degrees? 45 degrees. And what if we just wanted to, what if in our code we were just doing something like increasing theta, and so we just wanted our point to create an arc or a circle and just keep going around. That's what we'll do in our code to begin with. And so what we want is some kind of formula or function that, given theta, so we're going to give it a new angle, we could just increase theta each draw loop or update loop, animation loop. And so we want to give this function theta, and then we want to know what is the new location of x and what is the value for x, what is the value for y, giving us our new location. So that's polar coordinates, and that's in 2D. That's in 2D because we've just got this plane of x and y. For 3D, we want to just simply add z. So we want to add z. So let's go and do it in 2D first of all. So I've got an empty JavaScript file. I don't know if you've seen my 3D WebGL tutorials. I think I've made 3 tutorials at the moment. So I'm just building it inside that same folder because we want to be able to use 3D polar coordinates to have planets or moons orbiting around a central body. It'd be really useful to just have a radius for how far away the moon or the planet is away from its origin planet that it's orbiting around. So we've got a radius, and then we just want to give it a new angle, keep updating that, and we want a formula to work out where its new x, y, and z values are, where its new location is. And then we can do rotations and things much more easily than using the rotation function and translate, which means you have to kind of nest different rotations, and they often go wrong and very difficult. If we just have a formula to tell us where x, y, and z are, it'll be a lot easier. Let's start in 2D. So we're just going to set up, I'm going to use P5, use the P5.js library, which allows us to do graphics and input very, very easily. So the P5 library will start things going with a setup function, and we can create a canvas on our HTML page, and let's just have, I don't know, 512 by 512 pixels on our canvas, and let's make it, I don't know, a random color. Background is a P5 function to choose a color, and you put in red component, a green component, and a blue component. So 213 and 44. So I just picked those by random, save this, and now we can have a draw. We could have a draw loop. Yes, because we want to animate like a clock face or something. So P5 asks for a draw loop as well. When it spots that draw loop, that draw function, it will loop it for us over and over. So let's just see if we've got a canvas that is this random color. Okay, it's kind of like a nice red. Okay, I'll bring that over there. So things are working, and I've got my title ready, polar coordinates in 2D and 3D. Right, so let's just have a point now. Let's have an x equals 0, let y equals 0, and we want an angle, so let's call that theta equals 0. Okay. Oh, we need a radius. Look. We need a radius here. We need a radius. Right. So let r equal, what should we have? I don't know, 112? Just popped into my head. Okay, right. So let's see if we can determine where x and y are just from our angle and our radius. So let's have a function to go and draw that. So what do we want to call it? We want to call it something like find x, y, please. And we could pass into that function our angle, although it's a global angle, so let's not. Right, or should I be... No, it's going to be tidy. Let's just keep things simple. Right, so now here's our formula. Here's our polar coordinate formula. So polar coordinate formula. So we want to find x and y. So x is going to equal our origin point. Now we need an origin point. So that's just going to be the middle of the canvas, let's say. So that's going to be, in terms of x, it's going to be the width of the canvas divided by 2. And P5 gives you the width keyword. After you've created a canvas, it will record whatever size canvas you've got in the width variable. So width divided by 2, so that's halfway across, plus r, so that's the radius, times, now we need a math function. We need to access cosine. So in vanilla JavaScript, you should have access to math.cos, will give you cosine, and then we're going to put in theta. There we go. Now, shall I say this now? Yes, I shall. Things aren't quite as simple as that, because this cosine, I don't know if it actually tells us when we write cosine. Oh, well, I'll tell you now. I don't have to do it. The cosine function takes radians, And so we're thinking of theta in terms of degrees. So to convert to radians, it's as simple as just writing radians. I think this is with P5. You can write radians and put the number, the value or the variable that you're using to record degrees in here. So I'm thinking in terms of degrees with theta. So I'm thinking of 360 is going all the way around. So I'm going to convert to radians. Okay, that's the bit of the formula for finding out our new x location. So y is going to be not the width divided by height. So we want to move from the origin point first. We want to start our formula from the origin point. So height divided by 2 plus r, so that's the same, multiplied by, now this time we want sine. So we'll just write math sin, and then we're going to put in theta again. So we'll convert to radians, because that's what the sine function is expecting. And I'm going to give it degrees, or I'm thinking in degrees. And there we go. So our find x and y, it changes, actually it does more than find them, it changes x and y given theta and given a radius. So the radius is not going to change, although it would be fun to kind of change the radius as we go round. I don't think I've ever done that. Right, so I might do that. So in the draw loop, let's actually animate something. Maybe make some spaces so this goes to the top so you can see it easily. So the first thing I want to do in the draw loop is redraw the background over everything and then draw our object, so we get the illusion of animation. So background we want to be the same. Got this weird red colour, which I chose by random. There you go. Get in there, get in there. Right. And now we want to draw this point. So in P5 you can draw a point by writing point. Instead of that, let's draw a line from the origin to the point. So to do that in P5, you write line, and then the first two parameters are where you want the line to start, and the second two parameters where you want that line to stop. Okay, so x and y first. So let's say, now we need the origin. So that's going to be width divided by 2, height divided by 2. And we want the end of the line to be our x and y. There we go. Now, before we draw that, we want to go and find x and y. Not find xp. xp's gone. History. X and y. So let's just see if this works. Let's just see what we've got. We should have some kind of white line, I guess, drawn. It'll be interesting to see where it draws it. Will it draw it vertically, or will it draw it this way, horizontally? Or will it do nothing and crash? Ah, it did the maths thing. It did the maths thing. So here's our origin, half, so width divided by 2, height divided by 2, and it's drawn it there. I think we need to thicken up this line. I apologise if you can't see it. I think you will be able to with the resolution. So before we draw anything, in P5, we're dealing with a line, and so that's called stroke in many drawing programs, and stroke weight refers to how heavy or thick the line's going to be. So let's make that a cheeky 7, and then let's make it white so that we can actually see it. Or what's the opposite of red? Is it green? So red 0, red, green, 255, and just a little bit of blue to keep everybody happy. A little bit of blue. Okay, so can we see our line a little bit better? Drawn from the origin to the right. So this is the end of our line. So now what we want to do is increase, not the radius, we'll do that later, but increase theta, the angle. And will it go counterclockwise if I increase it? Let's see. So what we could just say, before we find x and y in our draw loop, we could just say r++, and that would increase it by 1. But that would be a little boring. So, and not very interactive. So P5 gives us a nice input, very easy input function. Let's say mouse dragged. And I think this would work on a touch screen if you kind of touch the screen and then drag your finger along. Mouse drag. So if we're mouse dragging, then we can say R++. So it's interactive. And hopefully we'll have a little spinning line. That's the idea. Let's have a look. Okay, I'm moving my mouse, but it's not spinning around. I'm dragging now. Okay. That is unexpected. Oh! You've just been watching me talk about R. Why was I talking about R? I need theta to increase. I hope you enjoyed that train wreck, watching that happen. Right, here we go. Theta, so the angle we want to increase. That was really confusing for me. Right, okay. Oh, it's working. So I'm dragging and theta is increasing. The angle keeps increasing. So that's kind of cool. That's how you could achieve lots of interesting effects, interactions, and it's got some maths. So if you wanted to go the other way, minus minus. What if we wanted to start at the top? Then theta wants to be, I'm thinking in degrees. Now it's helpful that I don't have to think in radians. I'm not used to thinking in radians. So theta would be, if we're going that way, counterclockwise, then I guess it would be minus 90 degrees, and that would start us at the top. Let's just have a look. I think in radians, what would it be? It would be pi over 4, is that right? Pi divided by 2 is 90, yeah. Right, so that's how to get us started at the top. Oh, we're going left. I wanted to go the other way. What's happening here? Oh, I think it was going clockwise to begin with. Yeah, it was. I just forgot. There we go. So that's working like a clock. Brilliant. Let's just change R. This has no bearing on polar coordinates. We're done with 2D polar coordinates. And they're the functions, they're the equations that you want. Your origin point plus R times math cos, and it usually takes radians. And then the Y position, it's sine theta is what you input into the formula. So there we go. Yes, let's change R. Let's say R plus equals, let's use sine again, because sine is a wave like this, so it'll be nice to have R changing in a smooth way. So let's say sine, and let's say, I don't know, theta divided by 2. Oh, and I need to put in radians. Let's see what happens when I don't put in radians. Let's see what happens there. Okay. We've got this nice little wiggle. That's kind of cool. So that's how to get a wiggly clock. This is how to make a wiggly clock. Brilliant. Okay. Right. We need to go into the 3D world now. So let's use a sketch to, I don't know, make a kind of a weird 3D. Oh, let's get a planet rotating in 3D. Okay, so right, first thing we need to do is use WebGL. So P5 allows us to simply add to our create canvas function in capitals WebGL, and that tells P5 to create a canvas that has 3 dimensions. Okay, Background works exactly the same. I think 2D drawing is supposed to work. So it'd be very interesting if this works already, but we have a 3D drawing space. Okay, so the first thing we've got is difference, is that our line has been drawn down here. So somehow this equals width divided by 2. That's probably because, hopefully this will still work. Can we get all the way around? Oh, yep, here we come. Well, that's cool. So in a 3D space scene, you can still use 2D drawings and things. I wonder if does that mean I can draw a 3D line? Can I just change can I add a Z? I don't know about this. I'll try it. I was just talking about the coordinate system. So in 2D coordinates, up at the top is 0, 0. In 3D coordinates, this is 0, 0. So we want to change our origin to 0, 0. What might be better is to have a variable now for our origin. So let's write OX and OY. So that will be our origin point. In other words, back to our diagram. Let's use red. Is that red? Kind of a red, salmon. At our origin point, the center of the coordinates, that's going to be OX, OY. Okay, back to our code. And when we draw things, we want to draw from the origin point. Now that we've got our origin point as a variable, which we have to make at the top, you could easily imagine moving the origin point, but your spinning thing will stay relative to that origin point. In fact, let's just demonstrate that. So we need let OX equals 0, let OY equal 0. So 3D space 0, 0 will be the center of our canvas now. What we could do is move our origin point with the mouse, and let's just increase theta all the time, because that would look better. That would look better when we're just moving around the mouse. So this time in the draw loop, let's say theta plus plus. There we go. And let's say our origin x equals mouse x. So in P5, we can use the keyword mouse x to give us the mouse location on the x-axis, and OY will be mouse y. Okay. So now we should be able to, it's like we've made a little futuristic cursor or something like that. Oh, it's kind of offset. Oh, again, we've got the problem of the mouse x and mouse y works with 2D coordinates, and we're drawing in 3D space. So we need to minus width divided by 2 minus height divided by 2. That seems to be the offset. So OX equals width divided by 2, and mouse y is is height divided by 2. There we go. Let's just see that. Oh, minus that, minus that. There we go. Okay. And hopefully now we've got our, center of orbit, or our origin for x and y, in the middle of the cursor. Okay. I'm not sure that we've got our wiggle working anymore. Oh, was that only working when, we were dragging the mouse? So the wiggle, the sine wiggle that we used is only working when we're dragging the mouse. There we go. Right, so we are in 3D, so I'm very curious to see, maybe before we draw let's draw the planet, and then I'll see if we can draw a line in 3D. I didn't know you could do that, or if you can do that. So the first thing we'll do is draw a planet in the middle of the screen. So to do that, now that we've got a 3D canvas, we write sphere. How large your sphere wants to be. Let's just go for 100. And we need a position. So we need to first translate. Well, you know what? If we just run it, let's just see if we've got a sphere first of all. Yes, we do. We've got a 3D sphere. Notice that the sphere is drawn with reference to the stroke weight and the stroke color. So we could change that before we draw our sphere. And also you can take off the stroke if you didn't like those lines. We have drawn it at the center of the canvas because the origin for when you're drawing is the center of the canvas. It is 0, 0, 0, X, Y, and Z. But if we wanted to move to a different location, we could say translate to, and let's just say 0, not width divided by 2, I'm thinking in 2D still, 0, and let's push it down a little bit. I think if you increase the number it goes down. Let's just try 100 and then nothing on the Z. Let's just see where that places our sphere. Okay, that makes sense. It moves our sphere down. So to take off the stroke, you just write no stroke. There we go. And the stroke will be turned back on when we draw our line. So we've already taken care of that. So our line should still be green, and we've got this 3D sphere. Interestingly, the line goes behind because it hasn't got a Z like component for where it's being drawn. But we are drawing the line first, so maybe P5 deals with things like that. It draws whatever you've drawn first behind, and then everything else you draw successively goes in front, as if they were layers. Right, we can make this sphere look a little bit better. I'm avoiding doing the 3D coordinates. I need to get on with that. I will put a link. I'll remember to put a link to this, or timestamp to the part where we get to the 3D coordinates. Let's just put an ambient. No, we'll put a specular material. Again, this is a P5 function. Specular material, and then you state what color you want. Let's go for blue. I don't think we've got much blue. Will that work? Or do we need to put a light in our scene? Yeah, we need a light in our scene as well. So we'll do that in setup. Let's place a light. Can I just put an ambient light in? No, I'll put a point light. Point light. And so to create a point light, first you tell P5 what color you would like. So I'm just going to make a white light so everything appears the correct color as I've determined it using strokes and specular materials. And then the position of your point light. So we want to have it towards the viewer. We do want it to be at 0, 0, so it's kind of in the center in terms of X and Y. But then Z location we want to come out towards the viewer, so that's positive on the Z axis, I think. So let's put it about 300 out, so it definitely shines in onto our scene. And our specular ball should look more, or planet, yes, it should look more specular. It's got a little, what do you call it, like a light spot on it now. Okay, right. One more, right, last bit of aesthetics. I want to increase the resolution of my sphere. So to do that, we can write two more parameters. By default, a sphere will have 24 segments in the X dimension and 16 in the Y. And so if you increase these numbers, we'll just do it by tenfold, then you have many more segments, and so a much smoother, more realistic ball. And the light spot will reflect that fact, metaphorically and literally. Right, so what we want to get is, let's say we'll make another tiny sphere and we'll translate to x, y, and z before we draw it according to 3D polar coordinates. Right, so these are a bit more complicated. So let's go back to our diagram, and I'll try and fit 3D down here. So this is going to be our 3D. So how do I start? So we're going to do the same thing. We're going to need R. We're going to need an origin point, X, Y, and Z. R is going to stay the same, and R is going to be, let's imagine this is in 3D space, so we've got a Z, we've got a set Z axis as well. So R is going to be constant, because we don't want our moon to get closer to the planet and then further away, unless you do want to do that, but I don't want to do that yet. And then we want to determine if we just increase theta, we want X to be different, Y then to be different, and Z to be different. So we need to find out what they are. But because we're in 3 dimensions, we've not only got this angle, we've got another angle that goes from, if you think about it, I'm struggling here, kind of in the Z dimension from the origin behind to the, like, kind of like, I'm struggling to say, to the Z location. I'm sure I could draw another diagram to make that clear. Another way of thinking about it is we've got another angle. So this one is called theta. So that's going to increase. And this one is called phi. And that's going to increase. I think what we can do now, if you wanted just to spin in 1 dimension, or according to 1 axis, so if we're spinning around like that, that would be according to the y-axis. We could just change, let's say, phi. But if we wanted to go, this way round, we would be rotating through the x-axis. So then we would have to change theta. We'd have to change theta. Okay. Right, so let's do that now. Let's do that. So now we need another function. Got ahead of myself. Function. Oh, this might be the timestamp, because now I'm writing the formula for x, y, and z. So function find x, y, z this time. Okay, so we'll say something like, if x-axis rotation, or orbit, so that's going around like this, x-axis, we want to increase theta, no, phi. If y-axis, x-axis, orbit, increase theta. Okay. So the formula, let's just jump into the formula. So it's going to be very similar to our 2D with some additions. And like with the 2D, I'm not going to explain the trigonometry, the mathematics behind it. This is simply to get your code working. So let's look at my notes so I get this right. X is going to be the origin point, so we'll call that OX, plus R, so far it's very similar, multiplied by, now we're going to say sine this time, so math sine, and then we're going to put theta, and then multiply this by math cosine phi. So 3D polar coordinates involve these 2 angles. That's why it's so much more complicated. So, but that's it for the x. It's not too long an equation. So y is going to be, y plus r, let's see if I can remember this, multiplied by math cosine sine theta, oh yes, times math sine phi L. There we go. So it's almost the same. X is sine cosine theta phi. Y is sine sine theta phi. Okay, so far so good. Z equals origin Z point plus r being our radius or orbital radius, times math dot cosine theta. There we go. So the Z dimension is only interested in theta, not phi. Okay, right. There are our formulae. Sorry, there are our equations, and let's see what we need to do. So let's comment out automatically increasing theta. Let's do it via the mouse drag again. And so let's change theta and see which orbit we get. R we don't want to change anymore. We don't want like a wobbly planet, although that would be interesting to play around with yourself. Crucially now, we want to translate our planet to, where do we want to go? Yeah, we want to go to, oh, we need a new planet. Sorry, we want to keep this planet here. And now we want to draw a new planet. Now, because we've translated to a certain point, this translation will affect the next translation that we do. So we can save our coordinate system that we get, that changes with the translate function, by using the push function. So that just saves the coordinate system. Then we can go and mess around with it as much as we like, draw our sphere, and then we can call pop. What that does is revert the coordinate system back to the last save point. So now 0, 0, 0, the origin is squarely in the middle of our scene where we're expecting it. So then when we draw our next 3D object, it will be on a level playing field where we expect it to be, and we're going to put push pop again, and then it won't affect anything else. Okay, so that's how you tend to do things in 3D graphics if you're having to use something like translate. Okay, so we want a baby moon, we want a moon. So we're going to say translate x, y, z, which are being determined in find x, y, and z. So we better call that here before we try and find that location. Okay, then let's have an ambient material. So ambient material won't be as reflective, it'll look like a smooth kind of matte object. Let's make you white. Can I go for white? 255. Oh yeah, that would look like a moon. Well, it might be grey, if memory serves. In this kind of lighting, you always get kind of grey object. And then finally our sphere. This is a bit dark now. Oh. Is that better? Okay. Right. Is that okay for lighting? I think that's okay. So sphere, and we want to be, let's say 25. Actually, I like 24. I like squarey kind of feeling numbers. So 24, and we'll leave its resolution at 2416, which is the default segment numbers or resolution there. Okay. Now I've lost kind of what we're doing in terms of our line. That's what I need. I need to write I need to add our Z variable for location, and we need our origin to be to have a Z component as well, and of course we need let phi equal, and 112 will be our radius, which is going to be a bit of a problem because our planet is 100 and our sphere is 24, and if it's only 112 away, I think 12 units of that planet, of that moon, will be inside the sphere. So let's make our sphere a bit smaller, our central planet. Let's make it something like 76, and we'll leave this at 24. So we've got phi. We've got phi. Now we'll put you at 0 and we'll put theta at 0. Now I'll be interested just to see if our find x, y, and z copes with theta and phi and r all starting at 0 except for the radius, because we could have theta as 0, but would that mean phi is going to be at 0? I don't know. Anyway, I've got a way to find out kind of the starting angles for theta and phi if you have, say, a point that you've already determined from like a vector or something like that. Anyway, I think we're just about to start. Oh, we don't want the origin to change. Oh, we could change the origin. We could change the origin of our planet. So I'm just thinking that our origin x and OX and OY and OZ are going to be affected by the mouse. So our origin for our planet wants to be our sphere's origin, which is 76, 240, 160. So do I just add, shall I just add that in here? Okay, I'll just hard code it for now. 76, 240, 250. Oh, what am I talking about? Sorry. It's getting too late. It's getting late. This is just the size of our sphere. That's why my brain was trying to stop me. Sorry, 0, 100, 0. Are the origin points. 0, 100, 0. Okay, let's do that. So our planet won't be moving. We'll just keep it static. And our moon will be moving. And that means we can still have our mouse moving around. Right, I can't remember if I need to add anything else. Let's just see if we get anything working at all. So we've got our moon. It looks like it's on the outside edge of our planet. It looks like it's kind of close enough. Now, I think if I go back to the code, in mouse dragged, I'm going to increase theta. So each time we find x, y, and z to translate to the new x, y, and z before we draw our sphere, we should get new results for x, y, and z. Right. So let's start dragging. Wow. Okay. We've got the moon orbiting around, but it's going at an amazing pace. This might be because in our equation, our 3D polar coordinates, we didn't use radians. This might be the reason. Radians. So to convert to radians, we can use a p5 function, radians, and you pass in the number that you want to convert. final one. There we go. Oh, missed out a phi. Well done if you spotted that. Well done. Okay, save this and play. So if this is still too fast, which it isn't, which is good, we could slow down the rate at which theta increases. So let's just see if we can get away with changing phi. So mouse drag. Oh, I know. Now that I'm confident that works, let's increase theta there. Although we're going to use phi now. So phi plus plus. And remember, we should get movement on a different orbit. I think I've got things the wrong way round. Because I said y-axis orbit increase phi, but we got y-axis orbit and we were increasing theta. So I've got these the wrong way round. I do know that in maths, they say theta for one particular angle and phi is the other angle. And in physics, I think they say this is theta and that's phi. Which wasn't what's confusing me. I'm an idiot, so I don't understand any of that, but I do know that's the case. So let's have a look now. Oh no. We're getting a crazy orbit this time. So if you like this effect, there you go. What on earth is happening? That's amazing. It'd be nice to kind of leave a trail behind it. You get a really nice pattern. It's making its way all the way around. Wow. There you go. Right. So let's try and correct for this. What is happening there? So our x-axis rotation wasn't working. Oh, also we've got z-axis rotation. What if you wanted to go around like that? Yeah. What if you wanted z-axis? Yeah, how to do that. So hopefully I'll be able to show you. Right, we are increasing phi. Oh, I'll still increasing theta there. Oh, so maybe we're not moving at all. Okay, so we're not moving at all, and that's because we haven't positioned our moon in the right position to begin with. We've just put her out there. So we need to set x, y, and z to begin with at the right position. So we need to find theta and phi according to a position first. So we know we're 112 away from the planet. So, and what do we want to do? This time we want to rotate like this. So we want x and y to be 0, but we want z to be towards the viewer. So x and y we can leave. Let's try and put z 112 away. But now we need to find, now that we've changed the location of the moon, we need to find what what theta and phi are. So to do that, let's do it down here. So we can say theta equals acos. Oh, and we're going to need maths. Acos, and we need the z location of our planet, which is 112, and we're going to divide that by, what are we going to divide that by? Divide that by r, yes. So that's going to be 1. Is that right? Are my notes right? Vz divided by r? Yeah, I think that's right. Okay. So phi is going to be, let's get these indented right, is going to be math, and now we need a tan 2, and then we can just put in y and x. Okay, so y and x are going to be 0 and 0 at the minute. So that will set up where phi needs to be and where theta needs to be. And we've positioned our planet out. Will this work? I don't have great hope. So there's too much maths there. And no, our planet isn't moving. Let's increase theta. See what happens there. No, okay, that's still working. So let's position phi somewhere, let's position our planet somewhere different. Let's put it to the right hand side of our main planet. So let's say 112 on the x axis, in the x direction, 0y, 0z then, r still is 112, and this time, so this was the z position, and this is r. Is that right? My handwriting is so bad. Yeah, I think that's R. Okay. I'm just wondering now, because I could be fiddling around and doing it in vain because I just haven't remembered the maths. So it's y, which is 0, divided by x, which is 112. What are we increasing? We're increasing theta. Let's just see what happens with theta. We might get lucky, might get a different result. Oh, I hate it when I have that little record button there. Okay. Okay, so theta's still working for the y-axis. But what if we increase phi? I have no hope this will work. Oh, it is it's rotating on. It's rotating on this axis, on the z-axis. A very small amount. Okay. Right. There is a hack. So what we could do is, before we draw things, we could just use the rotation function to kind of flip things around. So if we're over here, let's rotate by the z-axis and see if we get a result. So before we translate, we'll rotate according to the z-axis, and we want to rotate, I think I have to use radians here. Oh, did I use radians? Yes, I did there. No, I don't need radians there. I don't need radians. Rotate Z, radians, what am I doing? By 90 on the z-axis. Is that right? Oh no, that's just twisting it around that way. Anyway, I'll stick to that just in case it is right. I want to rotate on the x-axis. Oh, so we've got some kind of result there. That's terrible. I'm doing something wrong. It's annoyingly rotating around an axis, but we haven't got our sphere in the middle of it. What am I doing wrong there? What am I doing wrong? Let's try x. Okay, it's rotating around in the correct way, around the origin of our scene, which suggests I've got something wrong in the code. I've just changed the code somehow. So the origin point should be our planet. Oh, of course. This is not relative to the origin point. Oh, it is though, because it is just from 0, 0, 0. Oh no, but our origin isn't 0, 0, 0 anymore. Our origin is, was it 100 on the y-axis? Yes, it was 100 on the y-axis. I forgot about this. Oh, that might also explain the rotation that we got before. Oh, so we might have got all our axes of rotation working finally. No, that seems wrong. It's still rotating from the center. 0, 0, 0. Oh, equals 100. Oh, so I suppose this needs to be 112. Sorry, 212 from the origin point. That's really annoying. Oh, is it getting closer? Yeah, x wants to be, oh no, x divided, no, it's y divided by x. So that is right. That's right. That's z. Oh, no, y, we haven't moved yet. Yeah, so we're positioning our moon to the right-hand side of our planet. So y will be 0, and x will be 112. This just gets us back where we started, I'm sure. Are you wrong? Oh, I don't know if I saved. Yep, I did save. That's so annoying. Oh, unless it's just perspective. No, I don't think it's just perspective. I think I've got this wrong. That looks like it's rotating around 0, 0, 0. Oh, maybe did I not change it? Are you screaming at the video saying you didn't change it down here? Ah, this is a problem with hard coding. I didn't change it down here. Right. So, no, that is, oh no, that is the origin of our planet. That's fine. Yeah. Let's just change that to 0. I don't know what I'm doing. Oh, I am rotating by the x axis. Yeah, so that's changing things. Okay. So basically what I'm getting mixed up with, and I won't try and debug it now because I need to bring this video to a close, but I'm messing around with too many origin points and things like this. So, one last thing to do, rotate by the y. Okay. So, that's how to use polar coordinates unsuccessfully. Oh, there is one thing I can show you. What if we wanted like a slightly different tilt to our orbit to make things look cool? If you're just consistent with your origin points, things like that, everything should go okay. It has for me in the past. I'm not quite sure what I was doing here. But what if you just wanted to add like a little bit of a skew? So let's have a tilt variable. Let tilt equal, and let's say pi divided by, so we want about 20 degrees, something like that, divided by 9. So I'm trying to think in radians. I don't know what I'm doing. So tilt, and what we can do in our find x, y, and z axis, we can change, or we can influence this equation. So let's say phi plus our tilt. And do I just want to do that there? Yeah, and I'll do it here as well. Plus tilt. So hopefully we'll just knock our orbit off a little bit. Nope. I've done something terribly wrong. Theta plus tilt, theta plus tilt. Oh, we're already in radians. Why didn't I just put 20 degrees? I don't know why. Tilt. Let's try that. What on earth is going wrong? Was it because I tried to use pi at the top? Did you just try to use pi constant? If so, you may want to move it to your sketch's setup function. Oh, I see. Okay. So I can only use I can only use pi down here. Okay. So that's what's actually wrong, not the fact that I used it in the radians part. Okay. And can you see there's a tilt now to our orbit? So you definitely can't do that in 2 dimensions, because now we've got the x-axis involved, we've got the y-axis involved for the height of our planet, and we've got of our moon, and we've got z involved as well. So we have got 3D coordinates working, and you do have access to the other axes of rotation with this system, but just don't be as stupid as I am with your origin points or whatever other bug I've made. Do leave in the comments if you know exactly what I've done wrong there. I apologise. Right. Okay, thanks very much for watching 2D and 3D polar coordinates. Goodbye.